are Chapter 9, Section 7, so we are not doing Section 6. You can read that for your fun and enjoyment if you would like. But we are going to move on to Section 7, and it deals a little bit with statistics. I have to start my calculator. Forgot my calculator. Let's get him started over there. All right. When we look at sets of data, what we are describing with the data are called individuals. Individuals we're describing. Maybe we're describing the heights of people. So you are each individuals with a certain specific height. The characteristic of the individual is the variable. So your height would be the variable on this scenario that I was talking about. You are the individuals being measured, and the variable is the height that we are measuring. There are two types of data that we can measure. We can measure a categorical value or variable, or a quantitative. A categorical is a class which words describe. They say like male or female, or seniors or juniors, or people from North America or South America, something like that. Quantitative is a number. I've been talking about height. That would be quantitative data. There'd be a number associated with the height. The categorical data, like they have right over here, such as diseases, leading causes of death in the United States in 2001. The top three: heart disease, cancer, stroke, and then everything else lumped right in there. So this is categorical data. So we are having groups based on words or categories. Now when let's read this sentence. The numbers of deaths and percentages, they are certainly numerical, they are numbers, but they are not the values of the variable. The variable is what is the disease, heart disease, cancer, etc. So it's the disease that describes the individual. You wouldn't say, oh, you died of 29%. That doesn't make any sense. You died of heart disease, or whatever it was. When we have charts or graphs, there are different charts or graphs that can be used to display data. A bar chart, and a bar chart deals with categorical data, like the ones we have right here: heart disease, cancer, stroke, other, etc. So that's called a bar chart when we have categories as our variables. A pie charts is just like a three-dimensional circle graph. And so they work exactly the same way. They give a certain percentage of the complete circle. Of the 360 degrees, we could figure out 29% of 360 is so many degrees, and we know how big to make that slice of that pie or that slice of the circle. You might see picture graphs. So if I was going to do the same idea with picture graphs, heart disease, I'm going to abbreviate it. I have heart disease, I have cancer, I have stroke, and other down here. Well, a picture graph means we use pictures. So I would draw a nice little heart. Isn't that cute? Whoops, my heart got smashed on that one. So the height of it, just like on the bar chart up here, is going to represent how many from heart disease. Cancer, what should we make cancer? It's this glob. So there we go. So there's cancer. Stroke. Maybe we make a lightning bolt. See, that stands for stroke. And other. I don't know what we're going to have other. X's. That's other. So a picture graph uses pictures. It's just like a bar chart, but it uses pictures to represent the different values that we have along. So different ways of representing data. We often will use what's called a stem plot or a stem and leaf plot to help us organize large data sets. Here we have the percentage of each state's population that was 65 years older or older in the last official census in the year 2000. Well, 2010 is the last one, but anyhow, this is from the year 2000. And these numbers are, what do they say, the percentage? The percentage of the population that was 65 or older. So here we have a whole bunch of states, hopefully there are 50 of them there, and we want to try to organize this in some way. Well, a stem plot, or a stem and leaf plot, they both refer to the same thing, is one way of doing this. The stem is going to be our first one or two digits, depending on how we like to set it up. And then the leaves are the other values. So if I have right here 13.0, then I'd go to 13 and put a 0. That stands for 13.0. So in this case, our leaves are the tenths. And then we have 5.7, so we have a 5, and then 0.7. And it allows us to organize this and get a graph in some way, it's a plot, but a picture that helps us understand, most of the states fall with what percentage are 65 or older? Yeah, they're right here in the 12 and 13. It's very easy for us to see, I can see most states are 12 or 13%. And then we also can say, wow, this is a very unusual state. It has a very low population that is old. Which state was that had a very low population that was old? Alaska. Any ideas why? Why does Alaska have such a young population? Yeah, old people don't want to go up there in the cold. They want to go down south where it's warm and they can have nice warm winters. In fact, there's one state that really stands out with a high percentage of their population. It's Arkansas? I don't know. Find it. 17.6. Can you find it up there? Well, Florida. So, kind of the same reason as Alaska has so few, Florida has so many. They all want to go down to retire in Florida where it's warm all year. And all they have to worry about is hurricanes. I don't know. But you can see the stem and leaf plot is a nice quick way to organize data to see how your values are laid out. Before we had computers to figure out grades, and even though when I started teaching we did have computers then too, but it wasn't near as common. We didn't have all computerized grade books. A lot of times we did grades by hand, and I very often did stem and leaf plots from a test or from students' grades, and I could tell, hey, where do they all fall in the categories? So it's a nice, quick, and easy way to organize a bunch of data to kind of get a picture of how that data is laid out. Okay, so here's another one. They say, making a stem and leaf plot, the per capita federal aid. So how much does the federal government give in aid to state and local governments? The top 15 states, they say. This happens to be from 2003. And they want us to make a stem plots that provides a good visualization. I was talking about how it makes a good picture, a good visualization of those data. Then we're going to answer some questions. So looking at this one, what they have decided to do is, instead of taking all these values, let's just round this off. So this is approximately 3,700 for that state. So their stem is going to be the thousands place, and then the leaf is going to be the rounded off hundreds place. So for Alabama, 3,700, so there's Alabama, 3,700. And then we have what? Wyoming, 2,829, so that's 2,800 if we round it off. So 2,8, there's Alabama, right over there, 2,800. So they've made this stem and leaf plot. Now that we have this nice stem and leaf plot, it's very easy to visualize the data. They say, what is the average of the 15 numbers? Get your calculators out, and let's actually find the average. Let's do the actual values. So here we have a set right there, a set right there, a set right there, and there happen to be 15 of them. So go ahead and enter them all in, add them all together, divide by 15. Actual number, not the rounded, but the actual number. There are 15 of them. $1967? Still working? How's yours coming, Gio? Is that what you got in? All right. So there's our actual average, 1,967. Or if we were rounding it off like they were doing here, we would get 2,000 approximately if we were rounding off. But it's 1967, the actual value. Why is the stem plot a better summary of the data than the average? If you look at that for a minute, 2,000 is right here. Can any of you tell me why? Remember, an average is supposed to tell us what a normal state, the whole group, if we're picking one number, this one number describes all the states, what they are like. Too much difference? I want you to look right here. Notice we have a whole string of states that fit in this category of 1500 to 1900, right in here. And 2000 is really a little bit high to describe most of the states. Sometimes the average is not a good number describing. Why is it not a good number? Jiwan, you mentioned we've got some that are real high. We have this one down here that's really high compared to the others. If you have one number that's very large, it's going to pull that average to be a bigger number than what most of the states are like, because you have this one state sitting way out there that's too big. So it kind of drags that average up higher, where that average, even though it's actually the average number, it's not a good description of most states. Most states are between 15 and 19,000 per capita. What is that? State of, must be in millions or something like that. I probably cut it off. Well, let's call it 1,000, I guess, right now. It's going to be more money than that. But most of the states are right in this range. And so that's why the average is not really a good number. It's a little too big. And we can kind of see that from the stem and leaf plot, the visualization. We can do a back-to-back stem plot or stem and leaf plot if we have two things that we want to compare that have the same variable that have numbers going with it. So this happens to be the Major League home run totals for two people, Mark McGwire and Barry Bonds. And it's through the years 1986 through the years 2001. So we're comparing the same variable, their home runs, and two different people. So they did a back-to-back stem and leaf plot. Now notice our smallest number is 3 down here, and we go all the way up to, is 73 our largest? It looks like 73 is our largest. We've got a 70 stuck in there. So they have chosen the stem to be the tens place. So 0, 1, 2, etc. So 3 is right over here on the left. They've done Mark McGwire, and on the right is Barry Bonds. So 0, 3. So there's the number 3. And then 73, well, 73 happened to be Barry Bonds. Mark McGwire was the 3. Barry Bonds was the 73. So you can see it's a split. It just goes two different directions. Now we can't compare any more than two things on a split stem and leaf plot, or it'd really get confusing. Trying to go up and down and sideways, I don't know. We just go left and right on it. So here we've laid it all out. So we have a visualization in our stem and leaf plot, our split stem and leaf plot. We have a visualization, or a back-to-back, and we are going to answer some questions. Mark McGwire, Barry Bonds, they entered the major leagues in 1986, the same year, and had overlapping careers until 2001. They both played through that, and then one of them played longer. Mark McGwire retired, Barry Bonds kept playing. During that period, they averaged 36.44 and 35.44 home runs a year. Are those numbers very close to each other in the number of home runs a year? Yeah, they are. 35 and 36. I mean, almost identical was their average. If I actually took all their numbers, divided by how many years, we get essentially the same value. But compare their annual home run totals with this back-to-back stem plot. Can you tell which player was actually more consistent? What do we mean by being consistent? If you're consistent, what does that mean? Steady. Stayed the same. More consistent. Which one stayed more the same in their home runs? Barry Bonds. Barry Bonds is grouped closer together. He is more consistent in his home run totals. Now you may notice some other interesting things from this here. When you look at Mark McGwire, I mean, he had 3 years where he didn't even reach 10 home runs. And then, I mean, he just exploded. He went all the way up to in the 40s and the 50s and the 60s and the 70s. I mean, here's Barry Bonds, never less than 10, never more than 50, always between 10 and 50, right in this group right here. And Mark McGwire way up here with these huge numbers until, how did Barry Bonds all of a sudden get to be a miracle home run hitter? Oh, certainly not. Yeah. He retired. Well, this is when they're both active players. It makes you a little suspicious about steroids, doesn't it? Yeah. In fact, it makes you a little suspicious of both of them. Both of them probably have used steroids. I think they both have gone to court for that. But anyway, you can start seeing some things from the numbers as you look at them, especially when you look at Barry Bonds. He was very consistent, but then, what in the world? 73. I mean, something like that? Once in a while I do see something like that when I grade, yeah. It can work both ways. A whole bunch of people do good, and then there's one person, ooh, scored almost nothing. Or the other way around. All right, next thing we're going to look at. So what we've been talking about different ways of displaying data. We have these different charts and graphs and stem plots. Now we're going to look at what are called frequency tables. Frequency table, frequency is the number of times something occurs. So a frequency table is going to show us the number of times things occur in a category. And the spread of this is called the frequency distribution, how it's distributed. So we're still taking the home run totals, and we're looking at Mark McGwire, because we got bothered by Barry Bonds' 73 home runs, I guess. And they have made a frequency table. So we have the categories of between 0 and 9, 10 to 19, 20 to 29, so the units, the 10s, the 20s, the 30s, etc., and how frequent he fell in that category, 3 times, 0 times, 2 times, 5 times, etc. And so, if we take this frequency table, from a frequency table, we can create what's called a histogram. Now, a histogram looks like a bar chart, or they say it's related to a stim plot. Well, it is. It's just like what a bar chart is to categorical data. It's called a histogram when it's quantitative data. We have quantitative data, the number of home runs. That's what our variable is, how many home runs. And it's the same idea as a bar chart when you have categorical data. Many times people call histograms bar charts because they think, oh, they are a bar chart. Well, they're not. They look very similar, but the categories are numbers instead of categories being word groupings to them. So let's see if we can do a histogram on our calculators. We'll learn how to do that. We're going to make a histogram here of Hank Aaron's annual home run. So there's a famous baseball player from a long time ago. Long before there were steroids, anything like that existed. So when baseball statistics meant something for those who are pure baseball fans. Now they said to do an interval width of 5. Right back up here when they were doing it, they did an interval width of 10. 0 to 9 is 10. 20 to 29 is 10. So that's an interval width of every 10. They want us to do an interval width of 5 down here. Well, the first thing we have to do is divide it up into a frequency distribution so we can see where all those values fall. So here are all the number of home runs. And our smallest number of home runs is 10, looks like our smallest. And we have to go all the way. What's our biggest number? Is it 47? Is that the biggest number? Looks like 10 to 47 is our biggest number. So if we're going to go by fives, notice they took 10 to 14. And they counted how many times it occurred, how many times the 10 to 14 occurred. They have a frequency of 3. Then 15 to 19, etc. So let's see if we can't do this. So get your calculators running. Gio, I'll loan you one here. And we are going to see if I can move it so that the recording has my calculator and all the data in it. There we go. That should do it. So we are going to go over to our list, and we are going to choose, stats. We're going to go over to our stats, and we are going to edit a list. So I'm going to hit clear and enter on my list 1, so I've cleared out that list. We are going to enter the number of home runs. So just start entering, 13, 27, etc. Now, we don't care what year it happened. We just want to know the categories of how many home runs he made in each of those categories. Probably all done, and I'm still entering. How many years do we have? Do you have 24 or 23? I've got 23 too, so hopefully I have the right number. 23 sets of data there. Okay, now let's go to our plot. So second stat plot. Oh, I'm going to hit y equals for a minute. I want to make sure, okay, I don't have anything in there. I don't want any other equation trying to mess this up. Second stat plot. So I enter on my stat plot. We want to turn it on. Now we're not doing a type of a scatter plot, which what we have graphed before. We have a histogram. Isn't that cool right over there? We're going to choose a histogram. So when I choose that, notice we only have one list of where our values are. List 1 happens to be where our values are located. Now I'm going to hit my window button. Oh, that's not what I wanted. Uh-oh, did I forget how to do this? Maybe I need to go back, and maybe it's the... Oh, it's not the frequency. Frequency is 1. I'm going to have to try this out for just a second. Well, see, we need to tell it. It is my window button. Why did that not do that when I went to my window button? See, I've got things down there in the bottom corner. What's that? Let's change it back to function mode. Let's see if that does what I need. When I hit my window button, there we go. And got it figured out for us. My X minimum. We have 10 as our minimum. Our X max, we're going all the way to 50. Remember, we decided our biggest one was 47, so we need to go all the way to 50. And our scale, here's how much we want to group them. We want to group them by 5s. So 10 to 14, those are 5 numbers, 10, 11, 12, 13, 14. Now, our Y minimum, this is going to show our graph, and I'm actually going to do a -1, because I want to be able to see my x-axis. Y max, well, what is our biggest value? 6 is the most we have. So I'm going to go to 7. So for Y max, I'm going to show 7. And my Y scales are going by 1s. There we go. Now when we hit our graph button, there it is. Here comes our nice histogram. I'm not sure what I'm still thinking about. Oh, I bet I have an equation out there. Y equals. I did. So let me get rid of those equations. Now go back to my graph. If you hit trace, notice it will put a flasher on our first bar in our histogram. Another thing of difference in a histogram and a bar chart is your histogram, the bars are right next to each other because they stand for a continuous set of numerical values. So between 10 and less than 15, so that's 10 to 14, our number is 3. And if I arrow to the right, we have 0 in the 15 to 20 range, 2 in the 20 to 25, etc. So there we have our nice histogram. So that's how you can make the histogram on your calculator. N is the number. So notice we were flashing right here on our 10 to less than 15, which would be 10 to 14, right up here. And the number we have in the category is 3. The number we have in the category is 3. And as you arrow over, it'll tell you 0, then 2, then 3, etc. as you arrow to the right on that. So that's how you can make a histogram on your calculator. Time plots. Time plots is when we're considered about years or time and values. So a time plot is going to reveal a trend over time. We get a line graph out of it, and that line graph called a time plot because we are graphing time, days down here on this, and values on the Y. This happens to be a stock market, the Dow Jones Industrial Average. When is it? 1999, the year 1999. So there's their right chart that's kind of going along. You can see what the Dow Jones Industrial Average is doing. So right down here, have your calculators ready. We're going to try this one. I'll get rid of that. We'll do it again. Draw a time plot. It says the table 9.9 gives the number of compact disc CD units shipped to retailers each year in the 13-year period between 1991 and 2003. The numbers are in millions. And it's net, so includes the sold minus the return, so it's the net units that went out. Display the data in a time plot, and then they say analyze the 13-year trend. So we want to then look at that trend and see what that trend appears to be telling us. Let's see if I can move it over and actually see. So this one we are going to need in our table 2 values. How can I do this where we can see everything? I'll just have to start it off to the right and then bring it back to the left, I guess. So see, I'll make you guys wait. So our stat again, we are going to edit again. I'm going to clear out several tables. Whoops. So the first one should be the year. Now, you can do 1991, or you can do something like 1, number of years since. So that's what I'm going to do. So I'm going to enter 1 through, what are our years? 2003? So 1 through 13. And then I'm going to come back and do our values. Oh, 881.9. All right, to get them all, well, it looks like I have 13 numbers at least. So we're supposed to do a time plot. So back to our stat plot. You guys are probably already there. Make sure it's on. Now our type is a line plot. So not a scatter plot, but a line plot. Our second one over. So we have 2 variables. My X's are my years, which I put in list 1. And my Y list are my CD sold, list 2. My marker, sure, marker a little square, that works just fine. Now I'm going to hit a zoom to stat on this one. Zoom, and we'll go stats. And we may have to adjust it, but it should give us at least a good starting point for our time. Whoa. Somebody made a mistake in their data. 1, 2, 3, the fourth from the end. Stat, edit. I've got a, 9442.5, 942.5, 942.5. All right. Now let me hit my graph. Whoops. Zoom to stat. Isn't that choice 9? There we go. So not too hard to tell that something went wrong with my picture. So they want us to analyze this. What do you notice as a trend over time with CD sales? Yeah, we're going up, and then all of a sudden we hit a peak and we start heading down. Where's our peak? Yeah, 2000. So we increase in sales until 2000. Then we decrease. Any ideas why? Yeah. CDs. You guys get music? Do you go down to the store and buy a CD to get your music? Depends what CD, but probably more often no is the answer to that question. Maybe once in a while, but probably more often no. My wife loves music. I like music too, but my wife loves music, and we have these shelves of CDs that we never get out. Because what did we do? Well, I digitized them for her, put them into MP3s. So it's all on her phone now. And she wants new things. Well, she just goes to iTunes and buys that one song, or maybe that album if she really likes the album. Yeah, CD sales are going away. So if you're in the CD manufacturing business, sorry. Table 910 gives a number of cassette units. Any of you have an audio cassette? Jamie does. Before CDs, it was cassettes. I mean, you needed a cassette player in your car, so you could pop in that cassette. Of course, before cassettes, there were 8 tracks. But anyway, technology changes. So here they talk about cassettes. So here's our cassettes. Each year, 13-year period, 1991 to 2003, the same period as those CDs that we were doing. They want us to do an overlapping trend. Let's go back to our calculators. And let's put in our CD sales. So if I go back to my stat and edit, list 3, let's make it our cassettes. When you go to your stat plot, choose your second stat plot, and we want a line plot still. And mine is list 1 versus list 3 automatically, which is what we wanted. Set yours, list 1 for the X's, still the years, and list 3. And then change your symbol. I used a square, now I'm going to use a plus, and if you have color, you change your color. Isn't that cool? And then we are going to graph this one, but nothing is showing up. Why? Yeah, I think I have it turned on. Oh, maybe I didn't. Look at that. There's another reason why I might not be seeing anything. All right. Stat plot. I thought I turned it on, but maybe I didn't. I didn't. Enter. Turn it on. I'm missing. I need to change my window some. We've got to go much smaller on my window. This thing goes all the way down to 17.2. So I'm going to do my Y minimum, and I'm just going to call it 10. Maybe I need to go a little lower on my window. We'll call our Y minimum 5. And then graph it out. There we go. So you can see that there is a big difference. What had happened? CDs had already started their decline now. Back here in 1991, it was essentially even. The number of CDs and the number of cassette tapes that were being sold for your music, just about the same. But CDs were going up and cassettes were going down. And then we already discovered the year 2000, CDs hit their peak. What they need to now have is MP3s. So we can compare that. So what's going to happen with MP3s? They're the ones that started low, and then they're taking off. And what do you think the future is going to happen for MP3s? They're going to keep going up?
They've already gone down.
Already gone down a lot? Right, but your phone has to play even an MP3. Oh, like an MP3 player. Oh, you're exactly right. Yeah, exactly right. The MP3 player itself has already dropped off. It had a very short-lived. Probably if we were doing the MP3 player itself, skyrocketed, and then it went right back down. Because nobody does that, because their phones is doing it all. So if you have an ing calculator, it's in color, red and blue. See right over here. That's today's stuff. Easy stuff. Just dealing with data. Yeah.